So now we're going to talk about a couple of experiments, and these are from a long time ago, like 1800s, early 1900s. And again, I'm not going to test you specifically on these experiments, but I think it's helpful to look back and have a general understanding of how some of these things were discovered. And it also causes me to just be in awe of these people. I mean, some of them were doing stuff before electricity was really known, and they're making all these cool discoveries about things that are too small to see. I mean, it's really kind of crazy. So a guy named J.J. Thomson constructed a cathode ray tube. Now, if any of you play Smash Brothers semi-professionally, you'll know that in order to have a really good game of Smash Brothers, you need a cathode ray, a CRT television, because it has less lag than like a plasma or a flat screen. CRT, cathode ray tube, same idea, okay? So the cathode ray tube here is a glass tube that's partially evacuated, so there's only a little bit of a gas in there, and we've got metal ends on both sides, and we can attach a voltage source and pass electricity through this gas that's in this tube. And from the picture here, you can see that it looks like there's a beam of light here. That's not a beam of light, it's the atoms in the gas getting excited by the electricity that's passing through them. So J.J. Thomson found that a beam of particles that he called cathode rays, because they came from the cathode, they moved from this negative end to the positive end. The negative end's the cathode, the positive end is the anode. And that beam of particles, see, I think it's on the next slide. The beam of particles had certain properties. Those particles traveled in straight lines, and that beam was the same regardless of what kind of metal he made the cathode out of. You could do it with copper or iron, didn't matter. The beam was the same. So those particles carried a negative electrical charge. Electric current, is a flow of negative charge. So there was something that had a negative charge that was going from one end of this tube to the other. Negative charge is a fundamental property of some particles. So we have to have a real quick lesson in electrical charge here. So you can have positive charges and negative charges. Opposite charges attract each other, and the same charges will repel each other. So these are electrical charges, but they behave in many ways like magnets do. We've all played around with magnets, right? And if you stick the right ends of the magnets together, they'll stick together. And if you turn one of them around, then it's almost impossible to push them together. And if you do manage to, they're just going to separate as soon as you let go. You guys played with magnets? They're kind of weird, huh? Magnetic fields act the same way as electrical fields. So like charges repel each other, and opposite charges attract each other. If we have a +1 charge and a -1 charge, they're going to be attracted to each other, and then together overall they'll have no charge. So they kind of cancel each other out. They add up to 0. So Thomson's studying these cathode rays, and he was able to measure the charge to mass ratio by deflecting them. So here's a different shape of a CRT, and here's the cathode. This is the anode over here, passing electricity. This is the anode right here, passing electricity through here to make these rays, and then there was a hole in the anode so that those rays could just keep going. And so they would go in a straight line, and they would hit a detector over here. He could cause that ray to move by using an electric field or a magnetic field. So here he could deflect it. And this really is the basis of a CRT television. It uses this ray to excite pixels on the screen, and the way it gives you that whole picture is it moves back and forth. It rasters very quickly, and that's the refresh rate on your device. And the faster it goes, the less glitching you have when you watch fast motion. So he was able to measure charge to mass ratio, and he found that it was negative 1.76 times 10 to the 8th coulombs per gram. A coulomb is a unit of electrical charge. Okay, awesome. Any questions? We're getting somewhere with this. So the implication there was that the particles of that cathode ray were about 2,000 times lighter than hydrogen. Hydrogen was the smallest known atom. But I thought atoms were indestructible. How can you have a particle that's smaller than the smallest atom? What? This was incredible. It implied that this indestructible atom could be chipped. You could break pieces off of it, right? So, got to rethink our theory about atoms. So he had discovered what later came to be called the electron, a small negatively charged particle present in all atoms. That's the reason it didn't matter what element he used. All atoms have elements. And so this was a beam of electrons that he was making. So this was the first evidence that atoms are actually, atoms have smaller particles in them, and that all elements are composed of the same small particles. So Millikan did an experiment. It's called Millikan's oil drop experiment. And he was able to figure out the charge on a single electron. So Thomson got the charge to mass ratio, but Millikan used that in combination with his experiment to find the charge on the electron. So this looks like, I don't know, what does that look like? Weird contraption, right? So what is this? So he's got this big container here. Here he has some oil and an atomizer. So that's like that thing you spray with a perfume and it makes little teeny tiny particles and then you get them all over yourself. So you can atomize the oil here, make it into very tiny droplets. And so you spray those in here, and of course they're going to fall, right? There's a little tiny hole here in the center of this plate, and so some of the particles will fall through the hole. Most of them are just going to land on top, and it's going to be an oily mess up there. But some of them are going to fall through the hole. Now he's got another plate down here, and he's applying an electric field here. He's got a positive charge here and a negative charge there. And so as the particles are falling, he's taking some ionizing radiation and zapping them, and that causes them to have a charge, a negative charge. If you adjust the plates here, the charges on the plates, you can get these particles to suspend in midair. They have a negative charge, they're repelled by the negative plate, they're attracted to the positive plate. It's got a light source here and a viewing microscope, because those things are little teeny tiny things. So that's the main idea. So now we'll watch, it's not a great video, but I think it's still helpful.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
Any questions? I do not expect you to understand all of that. He could figure out the mass of the oil particle by watching how fast it fell, because how fast a particle falls depends on the mass and gravity. Gravity's not changing. He could figure out the charge on a particle based on what sort of a field was necessary to suspend it in air, right? Having the mass and the charge, then where was I going with that? Well, yeah, that's later. So knowing the charge on this particle, then, he found that different particles had different charges because they're different sizes too. And some of them had, what it turns out is some of them had 1 electron on them, some had 2, some had 3 or 4. But if he took all of these charges, he found that they were multiples of the same number. And that's the charge on a single electron. And then using Thomson's ratio and the charge, he could figure out the mass. Now that mass, 9.1 times 10 to the minus 28, so that's 0.27091 grams. I mean, we just can't even conceive how tiny that is.
The mass of an electron,
No.
9.
So here it is in different words. Measuring the strength of the field to keep those drops from falling. Figured out the mass. And then he was able to calculate the charge on each drop. Using that number and the mass to charge ratio that Thomson got, he was able to get the mass of an electron, which is this tiny, tiny thing here.